Good afternoon, dear friends. Well, today we will be dealing with the subchapters 3.4 and 3.5 in our book by Chiang, Alpha Chang and Kevin Wainwright. The 3.4 is about the general market equilibrium. Here we will see a kind of models, set of models called general equilibrium models. We are making an introduction to general equilibrium models. And then in the 3.5, we will see a macro model, national income equilibrium model. In the general market equilibrium model, there are some assumptions. Of course, no good in an economy, in a real economy, no good stands alone. Goods can be either substitute or complementary or unrelated with respect to demand. And they can be substitutes, only substitutes with respect to supply. Of course, they can be considered as unrelated as well with respect to supply if in the supply equation the other good is not taken into account. But in general, the goods are substitutes with respect to supply, and they can be substitute, complementary, or unrelated with respect to demand. So, in a general equilibrium model, we have n supply equations and n demand equations. We have n goods and n markets. So the assumptions of this model is that we have n goods. It can be 2 or more than 2. N markets, it can be again 2 or more than 2 markets. And n supply equations and n demand equations. So there are more than one variables and equation, more than one goods and more than one markets and more than one supply and demand equations. And of course, there should be also n equilibrium conditions. These n equilibrium conditions can be written as QDI equals QSI, I going from 1 to n, which means in each market, at each market, the demand pertaining to this good, to this market, should be equal to the supply of this market. So quantity supplied, quantity demanded of this good should be equal to the quantity supplied of this good. These can be also expressed as n excess demand functions, like ED for excess demand, EDI excess demand in the ith market. So we can express it. It is defined as QDI minus QSI equals 0. So instead of writing QDI equals QSI, we can also write QDI minus QSI equals 0, which is the same thing. Or in n excess supplies. So excess supply is QS minus QD, the part of supply over the demand. So excess supply I means ESI means excess supply in the ith market for the ith good, which is defined as QSI minus QDI equals 0, which means the part of the quantity supplied over quantity demanded is 0, so they are equal. So both of these three expressions are, they say the same things, and they are equally valid. You can use one of them, any of them actually. QDI equals QSI, or QDI minus QSI equals 0, or QSI minus QDI equals 0. They mean the same thing. It's sufficient to use just one of them. And I, of course, goes from 1 to n, because there are n goods and markets in this economy. If there is a solution, there will be n equilibrium prices, Pi star, and n equilibrium quantities, Qi star, related to these. Of course, if all the markets can reach equilibrium, if the equilibrium can be reached in all markets altogether at the same time, simultaneously, then we will obtain as a solution I, so 1 to n, so I going from 1 to n, which means n number of Pi stars, the equilibrium prices, and n number of Qi stars, equilibrium quantities. One equilibrium price and one equilibrium quantity for each market. So in total, there will be n of them. You see? So a simple example is a two commodity market model. We have two commodities. The assumptions are two goods, two commodity. Good and commodity are the same thing. So we have two goods, two commodities, two markets, one market for each good, and two supplies and two demands. One supply and one demand equation for each market, for each good, and two equilibrium conditions, of course, an equilibrium condition for each good, each market. So we can express them in general like this. The first equation is QDI equals QSI, or alternatively, excess demand 1, QD1 equals QS1, sorry, QD1 equals QS1 is the first equation, the equilibrium condition of the first market, which means the first good. QDI and QSI. QDI is the quantity demanded of the first good. QD1 is the quantity demanded of the first good, and QS1 is the quantity supplied of the first good. So ED1 is the excess demand for the first good, ED1, which is definitionally equal to QD1 minus QS1 equals 0. So if excess demand is 0, the market is in equilibrium. There is no excess demand, no excess supply. Supply equals demand. This is equilibrium. This is the definition of the equilibrium. All right. So we have two behavioral equations here for the first market, the demand and supply equations. QD1 equals A0 plus A1 P1 plus A2 P2. QS1 equals B0 plus B1 P1 plus B2 P2. Note that in each demand and supply equations, both prices of the first and the second good exist. So they influence both the demand and supply according to this model. So both prices are in both demand and supply equations. The fourth equation is the equilibrium condition of the second market, second good. QD2 equals QS2, or alternatively, we can write it down as excess demand 2, ED2, is equal to QD2 minus QS2 equals 0. Both express the same thing. You can use this one or this one as you wish. And then we have two more behavioral equations, the demand equation for the second market, second good, and the supply equation for the second good, second market. The demand equation is QD2 equals alpha 0 plus alpha 1 P1 plus alpha 2 P2. QS2 is beta 0 plus beta 1 P1 plus beta 2 P2. So you see they are symmetrical. And both prices exist in all these demand and supply equations. So goods are not, by definition, unrelated. They can be unrelated, of course. For instance, if alpha 2 is 0, QD2 will be unrelated of the second good. Or, well, it would be meaningless. Of course, QD2 will be related with itself, but it can be, for instance, alpha 1 is 0. Then it means the price of the first good doesn't influence the quantity demand of the second good. QD2 in the QD2 equation, if the alpha 1 is 0, it means the goods are unrelated. All right, so if we replace the second and third equation in the first one, and fifth and sixth equations in the second one, in the fourth one, I mean, which means we replace the demand and supply equations of each market in its own equilibrium equation. So QD1 and QCS1 is substituted in QD1 equals QS1. So QD1 here and QS1 here, they are open forms. And then QD2 here and QS2 here. So the QD2 and QS2 will be replaced in the equilibrium condition of the second market. Replacing these and taking all the variables on the left-hand side and letting right-hand side 0, and just grouping the variables accordingly, we obtain these two equations. Here there is a little some symbols are mixed up, but in the presentation it's not like this. When the presentation is loaded in this program, it makes some funny things sometimes. In the presentation it's okay, and here it is it's readable as well. So what is it? For instance, this parenthesis should be a little bit further down as well to cover both these two equations, but it shifted. I don't know why. In the presentation, it's correct. All right. So what we obtain is these two equations, a0 minus b0 plus a1 minus b1 p1 plus a2 minus b2 p2 equals 0. And the second equation, a0 minus b0 plus a1, alpha 0 minus beta 0 plus alpha 1 minus beta 1 p1 plus alpha 2 minus beta 2 p2 equals 0. So we reduce this system of six simultaneous equations, in a system of two reduced equations. You see, only in prices. If these two equations are independent, then we can solve the equilibrium prices P1 and P2, of course. And then we make another replacement, another substitution, in order to make the model more visible, more sort of readable. Instead of alpha minus b, a0 minus b0, we say c0, a1 minus b1, c1, a2 minus b2, c2. So we express it like ci equals ai minus bi. And for the second equation, we replace by gammas. Gamma I equals alpha I minus beta I, which means gamma 0 would be alpha 0 minus beta 0, gamma 1 will be alpha 1 minus beta 1, and gamma 2 will be alpha 2 minus beta 2. I from 0 to 2, of course. And in this way, we obtain even a simpler model like this. The first equation is C0 plus C1 P1 plus C2 P2 equals 0 for the first market. And gamma 0 plus gamma 1 P1 plus gamma 2 P2 equals 0 for the second market. You see? And then we can put these constant terms to the right-hand side to obtain C1 P1 plus C2 P2 equals minus C0, and gamma 1 P1 plus gamma P2, gamma 2 P2 equals minus gamma 0. You see, we are simplifying and solving the model. So here you see it destroyed my, the program has changed my, well, here there was a soul sign, there was an arrow, it changed it for some reason, I don't know why. Anyway, then we, from the first equation, transformed first equation, we can draw P2 as minus, in parentheses, C1 plus C1, C0 plus C1 P1 over C2. We can obtain from, we can let P2 alone, minus C1, C0. When we put this C1 P1 to the other side, we obtain minus C0 minus C1 P1, and this taking minus in parentheses in factorizing, we can have minus times C1 C0 plus C1 P1, the whole divided by C2. So P2 can be drawn like this from the first equation, and then replacing this in the second equation and taking P2 P1, I mean, we obtain P1 star, and then replacing this in one of these equations, we obtain P2 star. When we make these replacements, these substitutions, it is by substitution, by replacement, that we make, we find the solution. So we obtain these solutions. Just make it as an exercise at home, and you will see that you will obtain these solutions when you replace, obtain P2 from this first equation as minus, in parentheses, C0 plus C1 P1 over C2, and replacing in the second one, the P2 disappears, you draw P1 star, and then replacing this in any of these equations, and drawing P2 star, you obtain P2 star. Both equilibrium prices can be obtained this way. P1 star is equal to C2 gamma 0 minus C0 gamma 2 over C1 gamma 2 minus C2 gamma 1. All right. And P2 star is equal to C0 gamma 1 minus C1 gamma 0 over C1 gamma 2 minus C2 gamma 1. Note that the denominators are the same. And of course, they should be the same. The whole system has one denominator, which, well, which is also a condition for the existence of the solution. The denominator must not be 0. That's to say, that means C1 gamma 2 should be different from C2 gamma 1 in order their difference to be different from 0. Otherwise, if the denominator is 0, these quantities would be undetermined. You can't determine, they will be undefined, undetermined. So C1 gamma 2 should be different from C2 gamma 1, you see. And this means geometrically, when we draw these lines, we obtain on a Cartesian coordinate system P1, P2, we obtain two lines intersecting each other. That the denominator is 0, that C1 gamma 2 is equal to C2 gamma 1, means they don't intersect at all, these lines. They are parallel and they intersect in the infinity. They don't intersect really. So you don't obtain a solution. That's why the denominator must not be 0. You see? Meaning that the lines must not be parallel and they must intersect. Oh, of course. And in order to, this is the first condition. We have another condition as well. The second condition is that these quantities should be positive in order to be interpreted as prices. Otherwise, we don't know what a negative price is, a negative quantity is. Prices and quantities for us are positive. Perhaps in the master's and PhD level, doctoral level, you can face some negative price and negative quantities, but not here. Apples and pears cannot be negative, and their prices are not negative. When you buy an apple, nobody gives you money, you give money and you buy apples. So both prices and quantities are positive for the moment for this course. So we deem that P1 star and P2 star must be positive, means their numerators and denominators should have the same sign. If the numerator is negative, the denominator should be negative. If the numerator is positive, the denominator should be as well, positive as well, so that their quotient, their division, would give a positive number, positive value for P1 star and P2 star. A negative price and negative quantities, negative prices and negative quantities are unacceptable. We don't accept negative price and negative quantities. We find them as solutions, but then we say economically unacceptable, economically meaningless, we say. You see? Here we can learn the signum function. We can use the signum function. Signum function is the sign. You see, signum is the Latin. In fact, the word sign comes from Latin signum, which means sign. And signum function is a function which returns, which gives a value of 1 for y if we put something positive in it. Meaning, if x is greater than 0, y equals signum x is equal to 1. If x is 0, y equals signum x function is equal to 0. And if x is negative, less than 0, then y equals signum x function returns a value of minus 1. It gives a y value of minus 1. So it has three values, 1, 0. You see? All right. So let's see. Then if the signum function, the sign function means the sign of it when it gives the value 1, it means x is positive, what is inside is positive. When it gives the value of 0, it means what is inside is 0. And when it gives a value of minus 1, it means what is inside, the argument of the function, is negative. So here we can express the fact that they should be, both numerator and denominator should have the same sign, can be expressed like this. Signum C2 gamma 0 minus C0 gamma 2, which is the numerator, equals signum C1 gamma 2 minus C2 gamma 1, denominator. So both signs of the numerator and denominator should be same. And it's the same for P2 star as well. Signum C0 gamma 1 minus C1 gamma 0 should be equal to signum C1 gamma 2 minus C2 gamma 1. Signum means sign. So then Let's see a numeric example. In the numeric example, we will have numeric coefficients, and we can solve the problem numerically. Which means finding the equilibrium prices and equilibrium quantities, P1 star, P2 star, and Q1 star, Q2 star. We'll find them. All right. So the first equation is the equilibrium condition, QD1 minus QS1, or QD1 equals, QD1 equals QS1, or in excess demand form, excess demand 1 equals QD1 minus QS1 equals 0. You can use either this form or this form. They are equivalent. So QD1, the demand equation for the first good, is 10 minus 2P1 plus P2. You see that both P1 and P2 appear in the demand equation for the first good. The first equation is the equilibrium condition for the first good for the first market. First good means first market. Second good means second market. Each we have one market for each good. So, and in the third equation, we see the supply equation for the first good for the first market, which is QS1 equals minus 2 plus 3P1. But here, we don't see P2. In fact, there is P2 here, but with a zero coefficient. We could have written this as QS1 equals minus 2 plus 3P1 plus 0 P2. Meaning that in the supply equation, the second good is not taken into account. The goods are unrelated according to supply. Can they be? Yes, they can be. It's a simplification, but they can be, of course. If the vendor, the supplier of the first good, doesn't take into account the price of the second good, it means they are unrelated for him or her. So we can well have an equation such that QS1 equals minus 2 plus 3P1 plus 0 P2, which we don't write. All right. Then the fourth equation is the equilibrium condition for the second market, second good, QD2 equals QS2, or equilibrium, the excess demand 2 equals QD2 minus QS2 equals 0. We use any of them, just this one or this one. Not both of them, of course, because they say the same thing. All right, you could also, if you wish, you could also write down excess supply 2 equals QS2 minus QD2 equals 0 as well. This is possible as well, as you wish. But it is so for further analysis, it would be perhaps better to express it in excess demand form anyway. Sometimes we use these excess demands rather than the open form of the equilibrium condition. So the fifth equation is the demand equation for the second good, and sixth equation is the supply equation of the second good. So the fifth equation is QD2 equals 15 plus P1 minus P2. Just note that both prices exist in the demand equation for the second good, so they are not unrelated. And in QS2, minus 1 plus 2P2 plus 0 P1, which means the vendor, the supplier of the second good as well, does not take into account the price of the first good. So for the supply, these goods are unrelated, but for the demands, they are related. How are they related? We can tell it from the coefficients of P1 and P2. In QD1 equation, the second equation, we have minus 2P1 as expected. When the price of a good augments, its demand diminishes normally, if it's a normal good. When the price of a good diminishes, its quantity demanded augments. We want to buy more of it when it becomes cheaper. So this is normal. And if they were complementary, these goods, the coefficient of P2 should have been 0 as well, which is not in this case. Because in the complementary goods, we use them together, these complementary goods, so that when the price of, for instance, the cars and gasoline, they are complementary, or the cars and tires, they are complementary. but tea and coffee are substitutes, for instance. Or car and let's say underground are supplementary. Either you take underground or you go with your car. Either you drink coffee or tea. They are substitutes. So, but coffee and sugar or tea and sugar are complementaries. We use them together. The cars and tires or cars and gasoline are complementary. We use them together. So if the gasoline price augments, then the demand for the cars diminishes as well. As if the price of the sugar augments, the quantity demanded for the coffee diminishes as well, or for the tea diminishes as well, because coffee and tea and sugar are complementary. But coffee and tea are substitute. If the price of coffee augments, we drink more tea. So demand for tea augments. They are in inverse signs. If the price of coffee diminishes, we just drink less tea and more coffee, because then the demand for tea would diminish. You see? So here it is the case. These are not complementary but substitutes, because the price of the own good in QD1, P1 is negative as expected, and QD2 minus P2, so the coefficient of P2 is negative as expected. These are normal goods. When their prices augment, their quantity demanded diminish. Normal. But when the price of the other good augments, P2 augments, the quantity demanded for the first good augments. So they are substitutes. When the price of the second good augments, we avoid the second good and we consume more of the first one. Equally, we have, or similarly, we have QD2 equals 15 plus P1 minus P2. Minus P2 is normal. The price of the own good should come with a negative coefficient. But the price of the other good, of the first good, in the quantity demanded of the second good, it comes with a positive coefficient, which means when the price of the first good augments, let's say tea augments, for instance, the quantity demanded for coffee augments as well. So they are positive. They are in positive relation. They are not in inverse relation. So, which means these goods are substitutes. We can see it from the signs of the coefficient for the demand. But for the supply, they are unrelated because the price of the other good doesn't appear in the supply of the first good, and vice versa in this, or similarly in the supply of the second good. The price of the first good doesn't appear here. So for the supply they are unrelated. For the demand they are substitutes. All right. And here, in fact, we can deduce from this that first and second goods are substitute goods. Here it summarizes what I told you now. Your homework will be, how can they be complementary or unrelated? Just discuss, make some other models where these goods are complementary or unrelated, both for demand. For supply, they can be at the limit they can be unrelated as here, or substitute. They can't be complementary. For the vendor, for the supplier, all goods are complementary indeed if it takes the other goods into account. Otherwise, they are unrelated. But if it takes the other goods into account, in a shop, you put more visible the goods whose prices augment in order to sell them more. So all the goods compete when the price augments. You want to, whatever, if it is coffee or tea, for the vendor it doesn't mean, I mean, he or she can drink more coffee or tea. He can be a coffee drinker or tea drinker, but when he sells them, he would be willing to sell more of the one which has a higher price, or whose price augments. You see, that's why they are supplementary for the supply. All right, substitutes for the supply. So replacing second and third equation in the first one and fifth and sixth equation in the fourth one, we obtain and we reduce the equations. The q's disappear. We are left with P1 and P2. So we are left with these two equations. The first one, the substituting second and third equation in the first one, we obtain 10 minus 2P1 plus P2 equals minus 2 plus 3P1. And fifth and sixth in the fourth equation, we obtain the second reduced equation. 15 plus P1 minus P2 equals minus 1 plus 2P2. All right. And putting all these P's on the left hand side and the numbers on the right hand side, or vice versa, as you wish. Here it makes the opposite, I guess. Yes. Here the author, or well, in the presentation, all the P's are put on the right hand side, and all the constant coefficients on the constant terms on the left hand side. Usually one makes the opposite, but here in the book it is like this, so I reported from the book. And we obtain 10 plus 2 equals 3P1 plus 2P1 minus P2. You see that here when we put minus 2P1 to the other side, it becomes plus 2P1. When we put P2 to the other side, it becomes minus P2, and so on. So we obtain these equations. You should, at home, as a homework, you should solve all these equations by yourself as well, to understand, to learn them well. All right. So what do we have here? 10 plus 2 equals 3P1 plus 2P1 minus P2, and 15 plus 1 equals 2P2 minus P1 plus P2. Just simplifying them, we obtain 10 plus 2 is 12. You see now it inverted. It put the P's prices on the left hand side and the constant term to the right hand side, which would be the correct order actually. The other one is correct as well. I mean, mathematically, it's algebraically it's correct, but the how can I say, the tradition of the mathematics wants that the endogenous variables should go to the left hand side, and the exogenous variables and constant to the right hand side. So the first equation becomes 3 plus 2P1, 5P1 minus P2 equals 12. And here we have 2P1 plus P2, 3P2, minus P1 plus 3 minus 1P1, which means minus P1 plus 3P2 equals 16. And then we can solve these. We can either derive, for instance, P2 from here and replace in the second equation, or we can just put them, these equations, one under the other, and multiplying by the suitable coefficients and adding them, we can make one of these variables disappear, and we are left with the solution of the other one. So if you make these calculations and solve the model, you will obtain P1 star equals 52 or 14, and P2 star equals 92 or 14. And replacing these in the demand or supply equations here, when you have the T1 star, P2 star, the equilibrium prices of both goods, you can replace in supply or demand equations and obtain the Q1 star and Q2 star. It's easier in this case, for this model, it's easier to replace them, to substitute them in the supply equations, because you have one variable less. So but it doesn't make a difference. You can replace them in demand or supply. It doesn't make a difference. You would obtain, if you make it correctly, you would obtain the same solution anyway. So you obtain Q1 star is 64 over 7 and Q2 star 85 over 7. These solutions are correct. I checked them. These are correct. So you should find the same solutions as well if you make the calculations again. So, and both, I mean, they are defined, their denominators are not zero, and they are all positive. P1 star, P2 star, Q1 star, Q2 star, all the equilibrium prices and quantities are all positive. So the solution is economically meaningful. You see, the solution, when we mean solution, it is all these. This is a quadruple, four tuple, which is P1 star, P2 star, Q1 star, Q2 star. When we find both the equilibrium prices and quantities for all the markets, then we say we find the solution. We could have found the equilibrium prices by a graphical method as well after reducing the model in two equations, as I said. Then we could have drawn, these two equations on a Cartesian coordinate system and see where they intersect. They would intersect at the point P1 star, P2 star indeed, and then obtain this, we could replace again P1 star, P2 star um, in the supply or demand equations and obtain the Q1 star, Q2 star. But we don't solve, of course, in general, we don't solve like this. We solve it algebraically. We don't use the graphs for solving. It's just too simple. And when you have more than two variables, you can't apply this method. So you're not responsible of these graphs, of course. But it is a way. It's possible. Now we come to the N commodity case, the general equilibrium model. So here we have more than two. We have N commodity. One supply, one demand, and one equilibrium condition for each commodity, each market. So in all, 3N equations. Let's see. The father of these type of models is Léon Walras. It's pronounced Léon Walras. He's a French well, he can be as well Swiss perhaps, but of French origin. An engineer who became an economist, one of the fathers of the modern economics, Léon Walras, and he is the father of the general equilibrium model. In fact, he was looking. His problem, he was looking for a price vector that would bring all the markets in an economy into equilibrium, which means the supply-demand quantities of N goods should be equal. That is why the price vector P is on the y-axis. You know that in the economics books, we put the price axis on the y-axis. It comes from these people, actually, from the late 18th century, early 19th century, perhaps, 19th century economists, authors, because their problem, and especially Léon Walras' problem, was to find a price vector, a unique price vector, which would bring all the N markets together in equilibrium, which means which would equate the supply and demand in each market simultaneously. That's why he put the price at the y-axis, at the vertical axis, and excess demands, in fact, in the horizontal axis. He taught this way. So the assumptions of this model is that there are N goods, N markets, N supply equations, and N demand equations, and N equilibrium conditions, of course. So I is from 1 to N. In order to express it simply, we can say I is going from 1 to N, 1, 2, 3, 4, etc., up to N, and then QDI, the demand equations for each good, each market, is QDI equals QDI P1 to P1, Pn. All the prices appear in all the demand equations. QDI is the demand, typical demand for the ith market, for the ith good. And it is influenced more or less, if it is unrelated. Some of the prices may have the coefficient 0, but they are over there. So quantity demanded of a market of a good depends on the prices of all the other goods as well. All the prices appear in the quantity demand equation. The same for supply as well. QSI is the supply, quantity supplied of the ith good in the ith market, and it is influenced by all the prices from P1 to Pn. You see, this is a shortcut way to show all these equations, the system. And we have also n equilibrium conditions, QDI equals QSI. So we have, for each market, we have three equations: one demand, one supply equations, which are behavioral equations, and one equilibrium condition. So, and if there are n markets, n times 3 is 3n equations. The whole model has 3n equations. So we have n excess demands as well. You can express this equilibrium condition as excess demands. So we can say n excess demands EDI equals QDI minus QSI equals 0. Or n excess supplies if you wish. ESI equals QSI minus QDI equals 0. So if there is a solution, which is not guaranteed, sometimes there is none. It depends on the nature of the equations. And we will examine this more. If the equations are independent and we have enough independent equations and for each variable, then we can solve it. Otherwise, we can face with other sort of other situations. We can have no solution at all or many solutions, more than one solution, infinitely many solutions for the model. So if there is a solution, there will be n equilibrium prices pi star, which means from p1 star to pn star. I represents these indices, pi star, and n equilibrium quantities qi star. In the previous example, we had P1 star, P2 star, Q1 star, Q2 star. Why? Because we had two markets. If there are n markets, if there are 10 markets, for instance, we will have 10 equilibrium prices and 10 equilibrium quantities. One equilibrium price and one equilibrium quantity for each market, for each good, you see. All right. So, supply and demand equations can be substituted in the equilibrium conditions, of course, as we did in the previous example. And so the model can be reduced to n equations. Of course, if we replace the QI, QDI, QSIs in the equilibrium conditions, all these demand and supply equations disappear. They are reduced in the equilibrium conditions, which are which we have n of them. And from there, n equilibrium prices can be solved, of course. We have n equations with n equilibrium prices, P1 to Pn. And if they are independent, if these equations are they are consistent and independent, we can solve n equilibrium prices, each one equilibrium price for each good, each market, of course. And from there, n equilibrium prices can be solved, of course. Afterwards, these can be used to solve n equilibrium quantities, replaced in equations, and we can obtain as well n equilibrium quantities as well. Nevertheless, the existence of the equilibrium depends on conditions, as I said, because there is not always that we can obtain solutions. We can have no solution case, one unique solution case, or an infinitely many solution case. We can have three different cases, three different situations. So, and we will come to that. The excess demand for EI, instead of ED, I guess Walra used Walra, since he's French. Used EI rather than EDI. So EI is equal to QDI as a function of P1 to Pn minus QSI as a function of P1 to Pn equals 0. So EI is a function of n prices, P1 to Pn. All these excess demands should be 0 at the same time, simultaneously. If they are 0 simultaneously, we obtain a equilibrium price vector, P star, which is P1 star to Pn star. This is a vector. Each equilibrium price is an entry of the vector. So we have a vector of n elements, P1 star to Pn star. And from there, we obtain the Q1 star to Qn star, the equilibrium quantities, and they form the equilibrium quantity vector Q star. You see? So here we come to an important law in economics, and also very similar, in fact, a parallel law in physics. You might have heard of Kirchhoff law in your physics lessons, the physics lectures, perhaps at the high school. This part is not mentioned in the book. This is my addition. This is my sort of, well, I think it's important to mention both Kirchhoff law and Walras law in economics and Kirchhoff law in physics together, because they say the same thing. Very interesting, since they show that in all the sciences one thinks the same way, but and applies the same or very similar methods to different subjects. The subject is different, but the way of thinking, the philosophy is the same. Let's see. Kirchhoff, the physicist, he says, in a system of, it's about electricity, electric circuits. In a system of electric circuits, the sum of the loads going in, which are sources of electricity, like batteries or generators, must be equal to the sum of the loads going out. Their use of electricity, like lamps or machines, motors, engines, whatever, which use electricity. So in a circuit, we have sub-circuits as well. And, if all the loads coming in of all the electricity, all the energy coming in is used, we have equilibrium, which is like demand and supply. Supply are the loads, are the electricity produced or stored somewhere that we use. Those are supply. And then the demands are are made by the lamps or engines, whatever they use electricity. You see, this constitutes the demand of the electricity, if you wish. But here he doesn't say supply and demand. He's not an economist. He's a physicist. So he uses loads and uses of these loads. Electricity loads, of course. Energy. All right. Then what does he say? Let's see. In a system of electric circuits, the sum of the loads going in, the sources, must be equal to the sum of the loads going out, uses. If n-1 circuits are in equilibrium, we have a total circuit consisting of n sub-circuits. This is the idea. If n-1, say, besides the last one, all the circuits, all the sub-circuits are in equilibrium, the nth circuit must be in equilibrium as well. If you have a surplus of energy in one circuit, you should have a deficit of energy in another circuit. Otherwise, you don't have equilibrium in the system. If the whole system is in equilibrium, if the whole network of electricity, all greater circuit is in equilibrium, then you should have all either all the circuits, all the sub-circuits in equilibrium, or if you have one sub-circuit, this last one, for instance, in disequilibrium, you should have an opposite disequilibrium in another circuit to equilibrate the whole system. Otherwise, the system is not in equilibrium. You see? Very interesting and very well, very well pointed. But what says Walras, our man, economist? In an economy with n markets, it should be not markets. There's an error here. It's markets. In an economy with n markets, if n-1 markets are in equilibrium, the nth one must be in equilibrium as well. You see the same thing. One is with electric circuits, the other one with markets. They say the same thing. That's to say, the nth market is dependent on the others. In fact, exactly. Why? Because if n-1 markets or circuits are in equilibrium, the nth one should be in equilibrium as well. So it should depend on the others. It can't be in disequilibrium while the others are in equilibrium. If it is in disequilibrium, there should be another disequilibrium in another sub-circuit or another sub-market, in another market, to equilibrate the other disequilibrium and put the whole system in equilibrium. You see, this is the logic. Therefore, the system can solve n-1 equilibrium prices, but the nth price cannot be solved. In fact, if we have n-1 independent consistent equations and the nth equation is dependent on them, this system can solve only n-1 solution of the variables, solution level of the value of the variables. And the nth variable cannot be solved with the system of n-1 independent equations. The nth equation is necessarily dependent on the remaining n-1, be it a electric circuit or an economic system. They behave, their logic is the same. You see? Wonderful, isn't it? So, and this last price, if we can't solve n prices, but n-1, then this last price is taken as 1. We assume that it is 1. We put a value of 1 to this last price we cannot solve in the system. And it is called a numéraire in French. Numéraire is a French word. It comes from French to English as well, numéraire, which means like unity. It is 1. It is assigned a value of 1. So all the other prices are measured according to this one, or in ratio to this one. So it is called a numéraire. For the system theory, we don't have time to go into the system theory, but it's a huge and very nice theory. The system of all systems, be it electrical or economic or whatever, electric, economic, or other physical systems, biological systems, whatever systems you wish, human or natural or whatever. All the systems, there is a system of systems, the science of systems. It's called the system theory, and the father is Ludwig von Bertalanffy. You know Ludwig van Beethoven, the musician. Ludwig von Bertalanffy, he is of Hungarian origin, a German scientist, but of Hungarian origin, and he made the theory of the all systems. So it's worth mentioning, it's worth reading as well. Ludwig von Bertalanffy, the system theory, as a general culture. All right. So the solution of a general equation system, in this case, I mentioned these three situations where you have no solution, unique solution, or infinitely many solutions. How they appear. Let's discuss a little bit this. First of all, numeric coefficients give numeric solutions. If we have a model with numeric coefficients, we can obtain numeric solutions. But if we have a model with only parametric coefficients without numbers, then we obtain a parametric solution, like formulae. All right. P1 star, Pi star, I from 1 to n, which means n equilibrium prices, would depend on these parameters from I1 to A1 to AN, whatever parameters there are in the models. Of course, expressing the equilibrium values of the endogenous variables in terms of exogenous variables and coefficients parameters. So these parameters should be exogenous. If you have an endogenous variable as a solution in the solution of another endogenous variable, the model is not yet solved. You have to solve it more. At the end, in the real solution, all the endogenous variables' equilibrium values should be expressed with the exogenous variables and parameters, you see. So Pi star is expressed as a function of A1 to AN, all these, and they can be even more or less exogenous parameters, I from 1 to n. So for each market, we should find an equilibrium price. Number of equations equals number of endogenous variables. This is what we learn at the high school. We say that if the number of equations in a model is equal to the number of endogenous variables, the variables of the model should be, we should be able to solve the model. It should be solvable, but it's not true. This does not guarantee the solution. we have some counter examples where we have, for instance, two variables and two equations, but we don't obtain the solution, or we have infinitely many solutions. So it is possible as well. You see. In fact, the rule is that we should have in hand in the model as many independent and consistent equations. Independent and consistent, note these two adjectives. Independent and consistent equations as a number of endogenous variables to be solved. Otherwise, the model has either no solution, or if it is inconsistent, and if it is consistent but dependent, then it will have infinitely many solutions. We will see them now. So one example is, you see, x plus, the first equation is x plus y equals 8, and the second equation is x plus y equals 9. There are two equations, two variables, x and y, but this equation is not solvable. You can't solve this equation. There is no solution because they are contradictory. X plus y cannot be at the same time equal to 8 and 9. It's either 8 or 9. So if you have two equations like this, x plus y equals 8 and x plus y equals 9, these are contradictory. They are inconsistent. So there is no solution. This is the case where there is no solution. If some of the equations of the model are inconsistent, then there is no solution. And inconsistency cannot be solved, of course. All right, the second case is we have 2x plus y equals 12, 4x plus 2y equals 24. Well, these equations are functionally dependent and consistent. What does it mean? This means that, in fact, the second equation is the double of the first equation. Is 2 times the first equation. 2x plus y equals 12, or 4x plus 2y equals 24. In fact, this means we have only one equation here. There are not two equations. We have one independent equation, and the second equation is 2 times the first one. So it is dependent over the first one. In fact, we have one independent equation and two variables to solve. What should we do? We can assign different values to x's, for instance, and for each value we assign to x, we obtain another y. So we have an infinitely many solutions. This equation, first 2x plus y equals 2 and 4x plus 2y equals 24 are the same. When you simplify 4x plus 2y plus 24 by 2, you obtain the first equation. So we have in hand really one equation, not two. The second one is dependent on the first one. So then we can say y is equal to 12 minus 2x, and for each value, if I assign 0 to x, for instance, 2 times 0 is 0, y equals 12 minus 0, 12. If I assign 1, for instance, to x, then 2 times 1 is 2, y equals 2 minus x, 2 minus 1, 2 minus 2, 12 minus 2, 2 times 1 is 2, 12 minus 2 is 10. If I assign minus 1 instead of 1, then I obtain here minus 2, but putting out the other side, minus 2 is plus 2, then I obtain y equals 12 plus 2, 14. You see, in this way, I can obtain infinitely many solutions. For each value I put to x, I assign to x, I obtain another value of y. So here we have infinitely many solutions. And another case here is this one. We have three equations, the third case. 2x plus 3y equals 58, y equals 18, and x plus y equals 20. So these equations are consistent, but one is redundant. If we say, for instance, x plus y is 20. If I multiply this with 2, 2x plus 2y equals 40. And if I add y equals 18, I obtain 2x plus 3y equals 40 plus 18, 58. You see, we obtain the third equation from the first equation from the second and the third one. Or alternatively, we can obtain any of these equations from the other ones. So we here we have one redundant equation. We can drop the first one or the second one or the third one. Both the remaining ones would give the same result anyway. The solution of this equation is y equals 18, y star equals 18. And if it is 18, then this is done. This is given. So y star equals 18. X plus 18 is 20. So x is 20 minus 18, 2. So x star is 2, y star is 18. The sum is 20. If I put here instead of x, if I put 2 and 18 here instead of y, 3 times 18 is 54. 2 times 2 is 4. 54 plus 2, 54 plus 4, 58. You see, these equations are consistent. But one is redundant. The remaining two are functionally independent and consistent. There is a unique solution, x star, y star, which is 2, 18, which we found. All right. So let's see. This is for the general equilibrium model. Now we come to the equilibrium in national income analysis, which is also another type of general equilibrium. Here we have again a shift in the level of the lines, but this is not like this in the presentation. In the presentation, this is correct. This program for somehow shifts a little bit the lines in some cases. So this is a Keynesian national income model, which is a macroeconomic model. We have two equations, very simple. The first equation is the equilibrium condition or the national income identity. It's called national income identity. It's a Keynesian model from John Maynard Keynes. The first equation is y equals c plus I0 plus G0. The zero subscript means exogenous. When we put a zero subscript under a variable, it means exogenous. It's given from outside. Endogenous is in the model. Y and C are the endogenous variables of this model. I0, G0, and A are the exogenous variables and parameters of the model. So, Y is equal to C plus I0 plus J0. G is, yes, G0. I0 plus G0. Y equals C plus I0 plus G0. Y is national income. C is aggregate consumption, which is the total consumption of the society, of the nation, if this society is a nation. It can be also world level as well. So, or a region. All right. So, Y is national income. C is aggregate consumption, which is the total consumption of the society. I0 is the I, in fact, is investment, the total investment, the aggregate investment of the society. And G is the aggregate government expenditure of the society, of the nation. All the government current expenditures. Investments, government expenditures are included in I, actually. Current expenditures of the government, like the wages they pay to us, for instance, to the functionaries, and all these other all the papers, the electricity, whatever, all the current expenditures of the government are included in here, and all the government and private investments are summed up in the investment item. So we have it is also a supply equals demand equation. Y is the supply of the whole society, what we produce in 1 year. This is the supply side. And these three items form the demand side. C is the demand, our demand for consumption. I is the investment demand. And G is the government expenditure demand of the government, you see. So these three form the aggregate demand. And Y is the aggregate supply. Aggregate means total. All right, and 0 is exogenous. So we have the total cake we produce in 1 year, which is the total, the value of all the goods and services we produce, the nation produces in 1 year. It is Y. What it consumes in Y is C, what it invests is I, and what it uses as government expenses is G. So Y is equal to C plus I0 plus G0. This here there is an assumption, a hidden assumption, that the economy is a closed one. It's not an open economy. It doesn't make any trade or any interaction with the world outside, with other economies, other nations, other countries. It's like an island economy. It just produces and consumes and uses all the uses by itself. There is no, I mean, no interaction with other countries, other economies. It's a simplification, of course, and it can be relaxed afterwards. So the second equation is C equals A plus BY. This is a behavioral equation, which is the consumption equation. The total consumption, the aggregate consumption of the society is the sum of two things. There is one item of consumption which is autonomous consumption. Autonomous of what? Of income, which doesn't depend on income. And another part which depends on income. And this one is formed of B times Y. What is B? B is a coefficient between 0 and 1. So which we meaning that we don't use the whole, we don't consume all of our output, and we cannot consume 0 of it either. So we should consume some of it, typically 80%, 90% of it, and save 10% or 20% of it for investment, for instance. You see? So this is also a behavioral equation. It's consumption behavior, consumption equation, total aggregate consumption equation, which is a behavioral equation. So, all right. What are the endogenous variables of the model? Y, national income, C, aggregate consumption, and the exogenous variables are I0, aggregate investment, and G0, government expenditure. A is exogenous as well, but it is more like a parameter. It is called autonomous consumption. All these I0, G0, I0, G0, and A are positive. They are big positive quantities, like billion Turkish liras or $1 billion. And B is a coefficient between 0 and 1. It is like 1/2, 8/10, 9/10, something like this. It's a ratio. It's a coefficient between 0 and 1. If we don't allow it to be 0 or 1, because if we allow B to be 1, it means we consume all our production, which is unrealistic. We should have some, we should save some of it to make investment. And 0 would be unrealistic as well, because it would mean we don't consume anything of our output, then we would die. We should consume, a nation also as a person should consume some of its produce, some of its product output we should consume, and then the rest we can invest, we can save anyway. Saving means to live, not to consume today, but to leave it for tomorrow, for the future, and for investing it. All right. And the exogenous parameters, there are also, besides exogenous variables, there are two exogenous parameters, which is A, autonomous consumption, and B, marginal propensity to consume out of income. This B has a name. It is called marginal propensity to consume out of income. So it is between 0 and 1, and typically about 80%. All right. These equations are functionally independent and coherent. You see here, there is nothing to be, there are two equations. They are not multiples of each other. You can't obtain one equation from the other one. So they are independent and they are coherent as well. So we can solve, the model has a unique solution. The equations are functionally independent and coherent. Thus, they give consistent, coherent, the same thing. Thus, they give a unique solution, Y star, C star. Y and C are the endogenous variables. Y star, C star are the equilibrium values, which are the solutions from the model of the simultaneous equations, which means we should find the values of Y and C which satisfy all the equations simultaneously at the same time. So what we do, we replace the second equation in the first one. Let's see. C equals a plus by. Here we can replace c by a plus by. We obtain y equals a plus by plus I0 plus G0. You see, by substitution. 2 in 1 gives y equals a plus by plus I0 plus G0. Then we, since I0 and G0 are exogenous and by is y and by are endogenous, we put all the endogenous variables at the left hand side. Y is already there and by passes to the left hand side with a sign. So we obtain y minus by equals a plus I0 plus G0. We factorize it. We put 1 minus b to the factor to the as a product. 1 minus b, it becomes 1 minus b times y equals a plus I0 plus G0. Then here we obtain, dividing, since b is not equal to 1, this is not equal to 0, then we can divide both parts of the equation by 1 minus b. 1 minus b and 1 minus b, they annihilate each other, and we remain with, it makes 1, and we remain with y star. At the other side, we obtain a0, a plus I0 plus G0 over 1 minus b, which is the solution of y star. This is the equilibrium value. And for C star, we can replace this y star in the consumption equation. We obtain C star equals a plus b times y star. And a plus b, this means a plus b times a plus I0 plus G0 over 1 minus b. Putting these in the same denominator, we should multiply b by 1 minus b here. In fact, here we should divide all these quantity by 1 minus b when we put in the same denominator. Then we obtain a times 1 minus b plus b times a plus I0 plus G0 all over 1 minus b. 1 minus b is the common denominator. And here again, we should have had these, well, in fact, here when we multiply, we obtain a minus ab plus ab plus b times I0 plus b times J0. AB and minus and plus AB, they annihilate each other, and we remain with a here plus b times I0 plus G0 all over the same denominator, 1 minus b. This line should be prolongated to the whole expression. So the whole expression is divided by 1 minus b. There's a mistake here. I will correct it before distributing this presentation to you. I cannot correct it in the record, but I can correct it in the presentation. I will do it. You should consider this sort of division line as the whole line, not part. And the 1 minus b is the common denominator. All right. Then, since b is between 0 and 1, then b is not equal to 1. We don't allow b to be 1. So, the denominator cannot be 0 if b is less than 1. Then this quantity should be, cannot be 0. So, the system is, the solutions exist. They are not undefined, undetermined. But since b is less than 1, 1 minus b will be greater than 1. So, and 1 minus b is not equal to 0. And besides, a, b, I0, G0 are all positive. A, I0, G0 are great, big positive quantities. B is between 0 and 1, but positive. So, when we see here, you see, y star is a plus I0 plus G0 over 1 minus b. And these quantities are all sort of big positive quantities. Their sum is a big positive quantity. 1 minus b is positive as well because b is less than 1. So positive over positive, positive divided by positive gives us positive. So y star is greater than 0. It is positive. And c star is a plus b times I0 plus G0 over 1 minus b. 1 minus b is positive as we said. B is less than 1, so by 1 minus b is positive. A is positive. I0, G0 great positive numbers, so their sum is positive, and B is positive as well. Their product is positive, everything is positive, and the sum of the numerator is positive. The denominator is positive, so positive by positive is positive, so C star is positive as well. That's why, I mean, we can interpret Y star as the aggregate product and C star as the aggregate consumption of the society. They are economically meaningful. If we obtain one of them negative, for instance, it wouldn't have been economically meaningful. We should obtain these quantities as positive, as we obtain now. Otherwise, they won't be economically meaningful. What does it mean? I mean, as a nation, we work all the year long and produce something. It can't be negative. It can't be zero either. We produce huge quantities of everything. So you see, and for C star, actually, for C star, it is the same for the consumption as well. It's a big positive quantity. So, well, today the lesson is finished. Thank you very much for your attention. So I stop recording and see you next week. Don't forget to revise the presentations and the records. All these records, and I put them in my YouTube channel as well. And you find these records in Turkish as well in my YouTube channel. Have a nice week all. Bye bye.